Imagine taking a flat, lifeless two-dimensional image and blowing it up into a landscape of floating 3D cubes. That's exactly what we are building today. By the end of this video, you'll see how we can read the pixels of a standard picture, spawn thousands of individual randomly rotating blocks based on their color and brightness, and then actually fly a virtual camera right through it in real time. To pull off this illusion, we have to build a complete 3D rendering pipeline from the ground up. We'll start by defining how to store 3D data in memory, essentially teaching our program what vectors and triangles actually are. From there, we'll figure out the trigonometry to simulate a virtual camera that we can freely steer through space. Then comes the real magic, the projection math that crushes our 3D world down onto a flat two-dimensional monitor. And finally, a custom pixel drawing routine to ensure everything renders in the correct order. Let's go! Before we can draw anything, we have to teach the computer how to understand 3D space. Everything starts with a simple vector, basically just an x, y, z that pinpoints a specific spot in the void. But points alone don't make a solid object. In 3D graphics, nothing is actually solid. Everything is just a hollow shell built out of flat two-dimensional triangles. By connecting 3 points, we create a single flat surface. If we take 12 of these triangles and stitch them together perfectly, we get our fundamental building block, a 3D cube. Once we have that perfect master cube, we can stamp out thousands of copies, translating and rotating each one into world space to build our massive landscape. But world is pretty boring if you can't explore it. That's where our virtual camera comes in. A digital camera isn't a physical lens, it's literally just a single point in space that keeps track of 2 things: where it's located and which way it's looking. When you move your mouse, we translate that input into pitch, which is looking up and down, and yaw, which is looking left and right. To actually fly through the world, we need to turn those angles into physical movement. We use trigonometry, specifically sine and cosine functions, to calculate the forward vector and the right vector based on exactly where you are currently looking. This means when you press the W key, we don't just blindly add to your Z coordinate. We use those directional vectors to slide your position forward along your direct line of sight, giving us that smooth, free-flight mechanic. We've talked about it several times on my channel, but let me say it again. The camera never actually moves. It is entirely mathematical illusion. Our screen is permanently locked at the center of the universe, looking straight ahead. To make it feel like we are walking forward, we grab the entire 3D world and drag it backward. To make it feel like we are looking left, we rotate the entire universe to the right. This is called transforming from world space to view space. For every single vertex of every single triangle, we first subtract the camera's current position to physically pull the world toward our origin point. Then, we apply those pitch and yaw rotations we calculated earlier to mathematically spin all those points around our static camera. By the end of this loop, every object in the world has been repositioned relative to your eyeballs, perfectly preparing the geometry to be projected into your flat monitor. Don't forget that if you want to hear more details about anything we are discussing here today, feel free to go through the channel. There are also computer graphics related playlists in the description, together with plenty of videos about mathematics. Check it out, after you finish this one, of course. Our world is positioned correctly around the camera, so we need to talk about performance. A cube has 6 faces, but from any given angle, you can only ever see a maximum of 3. Give it a try. Drawing the back of a cube that is facing away from us is a waste of CPU power. Let's not do that. We can use backface scarring. If you look at the rendering pipeline in the code, you will see us calculating what is called a normal vector. By taking 2 edges of a triangle, which we call line 1 and line 2 here, and performing an operation called the cross product, we get a new line that points straight out from the surface, showing us exactly which way the triangle is facing. Then we use the dot product. We compare this normal vector against the camera's line of sight. If the dot product is less than or equal to 0, The face is pointing away from us, and we simply throw it in the trash. But the dot product gives us another incredible tool, fake lightning. By defining a global light direction pointing down into our world, we can compare that light vector against the triangle's normal. Faces pointing directly at the light get full brightness, while faces angled away get heavily darkened through our intensity multiplier. This simple flat shading calculation is what gives our flat geometry the illusion of real 3D volume. Before we can finally draw these illuminated triangles to the screen, we run into a major physical problem. What happens when a triangle passes behind the camera's lens? Well, mathematically, things break down rapidly. Coordinates invert, stretching wildly across the screen, and if a vertex hits exactly zero depth, we get a division by zero. To fix this, we implement a near-clipping plane. Think of it as an invisible wall sitting just in front of your virtual eyes. As you can see here in the clip against z-plane helper function, we evaluate the z value of every point on a triangle. If a triangle crosses that boundary, we can't just delete it, or we would see entire polygons pop out of existence while we are flying through them. Instead, the code physically slices the geometry right at the clipping plane, intersecting the lines and turning the original shape into one or two smaller, perfectly safe triangles that only exist in front of the camera. With our geometry safely clipped and illuminated, it's time for the greatest trick in 3D graphics, perspective projection. How do we take coordinates floating in three-dimensional space and squash them onto completely flat 2D monitor? The secret lies in a single mathematical concept called the perspective divide. Take a look at the final projection math in the main update loop. For every vertex, we take its x and y coordinates, multiply them by our field of view scale, and then explicitly divide them by their z depth. That single division is the core of perspective. Because dividing by a larger number yields a smaller result, vertices with higher z values, meaning they are further away from the camera, naturally have their x and y coordinates pushed closer to the center of the screen. This makes distant objects shrink organically, perfectly mimicking human vision and giving us our final 2D screen coordinates ready to be painted as pixels. So we have our two-dimensional screen coordinates, but how do we actually paint them so that close objects properly block the objects behind them? The easiest method is the painter's algorithm, which means just sorting all the triangles from back to front and drawing them in order. But if you ever try that in dense environment, you know it fails terribly. As our randomly rotated cubes intersect and overlap with one another, sorting whole triangles completely breaks down, causing our geometry to glitch and flicker as faces fight for the front position. To fix this, we have to abandon basic drawing functions and build a custom rasterizer, which you can see happening inside the fill triangle with depth function. Instead of just drawing lines, our custom rasterizer casts a tight bounding box around the projected two-dimensional triangle on the screen. Then we iterate through every single pixel inside that box. Using a mathematical concept called edge functions, we check if the current pixel sits cleanly inside the borders of all three edges. If it does, we don't just paint it immediately. Those edge calculations double as barycentric weights, allowing us to mathematically determine the exact interpolated depth of that specific dot on the surface of the triangle. This brings us to our ultimate weapon, the Z buffer. During our initialization, we create a massive hidden array called depth buffer that perfectly matches our screen resolution, designed to remember the depth of every single pixel we draw. Because perspective heavily warps distance, we actually convert our depth into 1 divided by z, which allows us to accurately and linearly interpolate the depth across the flat screen space. Before we color a pixel, we check its calculated depth against our z buffer. If its inverted z value is higher, it means it is physically closer to the camera lens than whatever was drawn there before. We immediately override the depth record and stamp our pixel color onto the screen. This guarantees pixel-perfect depth sorting across our entire chaotic landscape, completely eliminating overlapping artifacts without ever having to sort a single triangle. In a professional setting, with GPU programming and graphics APIs, The Z buffer, or that buffer, is exactly how your hardware actually determines what should be seen and what should stay hidden behind. With all of our 3D math and depth sorting firmly locked in, we can finally bring our two-dimensional image to life. Inside the Init tab, we define a target resolution grid and load our picture into memory. We then loop through that grid, stepping across the image to sample it pixel by pixel. For every single dot we read, we extract its exact color data and immediately spawn a brand new three-dimensional cube in our virtual world, painting its faces in that exact same shade. We arrange these thousands of cubes into a massive grid, but a perfectly flat wall of block is just a blocky two-dimensional picture. I want to push it into third dimension. To achieve that physical texture, we calculate the overall brightness of each sampled pixel. By using that brightness value to alter the z-coordinate of the cube, we can push the lighter colored blocks aggressively forward toward the camera and let the darker blocks sink deep into the background, literally extruding the flat picture into physical terrain. And finally, to break up the rigid robotic feel of the grid, we inject a little chaos. As every block is spawned, we feed random values into its x, y, and z rotation variables. This tumbles every single cube on its center point, shattering the flat surface and giving us that beautiful artistic look. And there you have it. By weaving all of these fundamental concepts together, we have successfully built a pure CPU-driven 3D rendering engine from absolutely nothing. We can now take the static image and explode it into a massive environment of randomly rotated, perfectly depth sorted, and dynamically illuminated cubes, all while flying our virtual camera freely through the chaos. It is a raw, unfiltered look at the sheer mathematics that power modern computer graphics. If you want to jump into programming graphics but really don't know where to start, try it here. You can work your way up from a simple one-colored cube to a fully textured and lit one. That would be all for today. Thanks for watching. If you want to see more in the future, hit the subscribe button, and ciao!